Hi, this is Zheng Chen from the Math Department of University of Massachusetts Dartmouth. And this video is going to talk about accomplish module ODE solver. So in this video, we are going to talk about what is the goal of this module. And also we are going to talk about the method that is going to be designed here in this module. So here's the table of the contents. So let's start. So the goal of this this module is that the student need to study the ODE problems, and also need to study the solvers for ODE module, which are the numerical methods for solve initial value problems of ODEs. By ODEs, I mean the ordinary differential equations. And later I'm going to give you the problem, how the problem looks like, and some properties for the well-posed problem that we're going to solve. And here is how the GUI will look like eventually when the problem is finished, when the coding is finished. So they're going to look at this and how in another video, I have a demo, like how we run this and how you should finish the coding. So here, let's just focus on the thing here. What's are in this GUI. So for this GUI, the user will input the formula of the right-hand side function for the ODE problem, which is a function of solution y and time t. And also that is the formula you need to input here. And also the user need to put in the range of time so that you want to solve this ODE by default, it's going to from t equals 0 to t equals 2. And you have the freedom to change these two options. And also this is for the IVP problem, the initial value problem. So you need to specify what is initial value for this problem. So by default, we put in 0.05 here, and you can just modify it with the problem you have. And once the GUI is, once we finished design this GUI, the user should have the option to click on this drop-down list and use the solver, select the solver they want to use to simulate this problem. And for some problems, they need to figure out, they have the freedom to put in how many number of time steps they want to solve. They want to do the simulation. So by default, it's 100. And for some MATLAB built-in method, we don't have this requirement. So once the user put in everything here, they click on solve, they'll get solution plotted on the right-hand side in this part. So they will have the option to repeat plotting for different solver with different setup, and they can compare them by selecting different color for each run. And they can also just show the current plot for the current method by click on this, do not plot over old answers. So if they click on this, they will show just one run, one result at a time. If they uncheck the box here, they can do multiple run and compare them in the same figure. So once everything is finished, click on the close and the app will be closed. So that's what the GUI looks like. And the framework of this GUI is provided in an app file, which is called ODE solver ODE solver _app.ml app. And also together with this file in the same folder, there will be several M files, one M file for each solver that need to be finished. So the students will be provided with the folder that those M files are not finished. So the key sentence will be removed. So students need to learn the algorithm and fill in the blank. And for the advisor, they will be provided with a folder like with full M files. While the students need to finish all those files by fill in the blank, the key sentence, the key lines in the coding. They can fill in exactly the same way, or they can fill in with their own freedom, right? As long as the result is good, then that's okay. So the advisor will have the full version, and they can demonstrate how it looks like after everything is finished. But the students should only have access to the folder that was for the students. Okay, so here are some resources. Even though the GUI setup is not required for the students to learn or to finish for this module, but the students still have the freedom to check them out, to learn about it, and to add in different solvers that's not covered here. To do those things, the student need to learn a little bit about the GUI in MATLAB. So in the history, there are two ways to do that. The previous way is to use the guide, but this is going to be removed very soon. So we don't recommend this, but if you're really curious about that, here's the web page. We recommend you use the App Designer, which is a new tool, and that's going to be the future tool as well for editing the GUIs. So here is a short video that is going to show you how it looks like and how you work with that. So here are the resources for GUI in MATLAB. And also in this method, in this module, we're going to include a few numerical methods, not all of them, but we are going to include all this in the solver. So the first one is a forward order method. The second one is a Taylor method, which can be higher order. By the way, the forward order is first order. The Taylor method can be second order, third order. You have the option to choose which order you want to use. And also we include range cutter methods. Here we have 3 of them for the second orders. The second order midpoint method, the second order modified order method, second order Hume method. And for range cutter method, we also include order 4. So all this will be listed in details in this current file. And to serve the purpose that we want to use this app for ODE simulations, so it's good to include the MATLAB built-in solvers. So we also list here the ODE 4.5, ODE 1.5s, ODE 2.3, ODE 2.3s, ODE 2.3t, ODE 1.1.3. So if you want to add in more, you are free to modify this option here and the corresponding code in the main file. So the numbers 7 to 12 are the MATLAB built-in functions. So students do not need to code this up. They are already done pretty well for the MATLAB. So the student only need to work on the first 6 of them. And to help the students be able to do this, we are going to talk about these methods in this video. Yeah, so that's the goal. Okay, now let's see what is the IVP for the ODE. What is the problem I want to talk about? So the IVP of ODE, so for example, the first order, it looks like this. So this is the abstract version. So basically what you have is you want to describe the changing rate of something, say y, with respect to time, say t, equals to some function. That function can include the variable y and t, right? So that's the right-hand side, and the left side is changing rate. So this can be velocity, then y will be velocity, and t will be time. This can be many things. As long as it's changing rate, then you can use this module to, you can use this problem to describe that. So for the problem, you want to specify what is the initial value for this y, right? So, and then you want to solve what is the value for y later on to some point, to some final time. So that's the initial value problem for ODE, for ordinary differential equation. And we're not free to write everything, make up everything here. We need to, because if you write it freely, you probably will have some problem that's not well posed, which means you don't have a good solution. So theoretically, you don't have a good solution, then there's no hope that numerically you can have a good one, right? So we want to work on the good problem, and in mathematical language, it's called well posedness. So basically means we are going to have a solution, and we are going to have a unique solution so that you can have some guarantee you will have solution, and you only have one solution, right? You won't find the wrong one. And also we are going to have some well-posedness for this. Yeah, that's not required. So for most cases, you can find in some simulation, the problem, they probably already well-posed. If you really care about how to check on them, this is definition. And also we have some sufficient conditions so that this problem is well-posed. So basically you check on this f function, this right-hand side. As long as it is continuous and also satisfies some Lipschitz conditions in y, then you're good, right? So what is Lipschitz? What is Lipschitz continuous? Which means the changing rate of the function, the right-hand side, is kind of bounded by the changing rate of the y times some number. So if you can do this for any a pair of y1, y2, then you're good. So here are some examples. A sufficient condition so that f is Lipschitz in y is that you have some convex function. Oh, sorry, you have some convex set, and also if the function f is the partial derivative here is well defined, and that is bounded, then you're good, right? So this is some math knowledge that you can use to check if the problem is well posed, right? So this is the problem you want to solve. Okay, now let's move on to the numerical part, the solvers. The very first solver is called Euler method. And as you notice, we have forward Euler, backward Euler, if you have heard somewhere, and this is the method we're going to talk about. So how do we simulate things, simulate solution of ODE problem, right? So basically what you do is you break the time. Suppose you want to solve from A to B. You just break that into different points, right? You select a few points, and those are called mesh points in between. And you just move on from one point to the next point and keep moving until you reach the final time, right? So that's how you do this numerical simulation. And the size between, the distance between the neighboring mesh points are called step size. And if you choose these points equally spaced, then the step size is just the length of the range divided by the number of points, number of future points, right? So you have n+1 points, then you divided that by n because there are n cells in between, right? Between n+1 points. So that's the step size. Those are the jargon we are going to use for numerical simulation. And the goal here is we want to create some algorithm, some logic, so that you move from one step to the next step. We can find approximate values of this y. Let's use w because it's not exact y. Let's use w for them. So these w's will be a good approximation for the y's value at these ti's, these time steps, these mesh points. Well, for the Euler method, it's like we want to modify this by using the finite difference. So you say the next omega I+1 minus omega I divided by h, which is kind of like approximation for the derivative, equals to the f at ti omega I, right? If you set that up, then you can solve for omega I+1 by this. So this is like forward Euler. And what is good about this is like you can see this will tell you how you do the simulation. So initially set omega 0, which is the function's value at t equals t0 to be the initial value that's given, right? And then you can move on. You can from omega 0, which by setting I equals 0, this right-hand side, you can just purely evaluate those things and then assign this to be omega 1. And then you set the right-hand side I equals to 1. You can move on to omega 2 and omega 3, omega 4, omega 5 until omega n, right? That's how you do this forward Euler method. So you're moving forward. explicitly, right? Because each time you have explicit formula here to evaluate for omega I plus 1. And basically what we do here is we just use WI to approximate this term. But if we use FTI plus 1, omega I plus 1, that will give us the backward order. This is the backward order. So if you look at the difference between forward order and the backward order, you will notice here we have I plus 1 instead of I. And also, in order to solve for WI plus 1, you need to solve this equation, right? So each time you fill in the omega I and solve for WI plus 1. So that's the backward order. And here is an example that you can try with forward order. And this is the function we put in here in the GUI by default. This is the problem we put in here by default. So once you finish this part of coding, you can play with this example. And also the exact solution is this. So just in case you're curious about what is the exact solution of this ODE problem. We run the forward order until t equals to 2. And here will be the result. So you get 2 time steps, right? And you from T0 to T1, T1 to T2. So that's what solution looks like. So once you finish your code, you can look at here and try to see how your solution looks like. Is that right? And here's the algorithm. The input will be A, B, initial value, and step size, those things, or number of time steps. And the output will be the Y's and the T's, right? And here are the steps. So if you look at the fe.m that's provided for students, this is how it looks like. It's a function. And the input, the output are already written up. And also we have finished set up the T0, the initial time, the final time, number of time steps, right? So here you see that we assign all the T's. So that means the time steps are already set up, but you need to fill in what are the Y's, what are the omegas actually in our algorithm, right? So you need to figure out how you code the omegas here, which is basically this line, right? You need to think about how to code that up. Fill in the blank here for the y n plus 1. That will be the omega I plus 1 in the algorithm, right? So that's the only thing you need to fill in the blank to have the forward order method working in this GUI. So we have some theoretical error bound. If you're curious, here are the theory. And also if you care, because in numeric simulation, we know there's something called round-off error, and that will also affect the error for your algorithm. In case you're curious about that, here's the theory. So that's the forward order method. And the next one is the high order method, the Taylor method. The Taylor method is very similar to forward order, but in different way is the different ways that instead of using the function f, we actually use a Taylor method, Taylor expansion here. So in forward order, you can say the Taylor method of order n, we use something called Tn. And if that n is say 0, then which means you don't have this part, you only have f, then that will give you the forward order, right? So Taylor method is by using the Taylor polynomial of this function f with higher order terms, more and more terms, you're going to get more and more accurate simulation. So that's how we do. And Tn here is the derivative of f, and this is a total derivative, which means whenever you take the derivative with respect to t, you need to first take partial f, partial t, and then you take partial f, partial y times y prime t. So this is called the total derivative of f with respect to time, right? So for order 1, you have this, which is forward order. For order 2, you have one more term, which is the f, which you have to add in this f prime times h over 2, and this f prime is that total derivative. And for order 3, you need to add one more term, h squared over 6 times second order total derivative of f with respect to t. So you just need to take this total derivative of this term again, right? And again, we have some arrow term here. Yeah, just in case you're curious, there's something called the local truncation arrow, and how that change with respect to the time size h will show us the order. That's what the order means. Okay, so basically the higher the order is, the faster the arrow will shrink when you decrease the size h, the time step size. So here again, the same example. So the example here is want to use Taylor method of order 2, and to figure it out, we need to figure out what is T2, right? So T2 here is f time plus h over 2f prime. This is total derivative. And you need to first figure out what is this, right? This is the f. Then what is the f prime? What is total derivative there? So that's something to figure out, fill in the blank, and then you'll be able to finish Taylor method of order 2 for the simulation. So I had the code here, so the student can work on it by themselves. And once they finish the part, they run the method with order 2 and n equals 2, they will get the red one, the red result. And for comparison, the yellow one is the forward order. So what the student need to do, oh, by the way, here is another example with Taylor, with order 3, one more term to figure out, right? So for that one, you get this blue one, which is much better than the red one here, right? Compared to the exact solution. So that's the simulation. What is good thing? What is bad thing here? The good thing is this can be very accurate. So which means the order here can be very high, which means when you shrink the size or you increase the number of time steps, the error of the solution will decrease much faster for higher order method, right? The disadvantage is that the student need to figure out the total derivatives, which sometimes is a pain. So yeah, so that's the good thing and bad thing. But if you're really good at taking the total derivatives, then this is a good method. So here is what the student need to do. In this function for Taylor method, we have the option to fill in the order here. So it's better that the student can find out this total derivative numerically. So here I help the student set up a few things here. To find the total derivative, I cannot use the help of the symbolic calculation here. So the student need to install the symbolic toolbox to do that. But if the students have other ways to do, they can change this part. So basically this part is to code up the Taylor polynomial of order, the Tn, right? Suppose this is n, then this is going to be the Tn, which is assigned to this T0. So T0 here will be a MATLAB function, a function that's going to give you what is the Taylor polynomial of order, right? So that's part. And this is a total derivative for the previous function. And we can assign the total derivative of order I plus 1 here, store that as a vector. But then you need to figure out how you modify this TO to be the total derivative of order I plus 1, right? In this current loop is I plus 1, but out of this loop you will get order, right? Okay, so this will change that into the MATLAB function. And then the same thing as forward order, you need to fill in the blank here, like how you get YY n plus 1, right? So that's what students need to do. Okay, so that's what Taylor method. The next one is the range cutter method. The range cutter method Here, the motivation is we want to obtain some high order method, but we don't want to compute the derivative, especially total derivative, as in the Taylor method. So what we do is we try to approximate the Taylor polynomial Tn locally, right? So for that one, we need to use the help of Taylor theorem. So let's skip this part, this mathematical part. Just tell you what are the popular range cutter methods. So the very first one is a second order range cutter method. Basically here we work on the second order Taylor method, and we replace this T2, which includes some total derivative. We replace that with some approximation. So here is how we approximate that. So let's just remove this math part and tell you the results. There are a lot of options. One option is to use some midpoint technology in some interval. And then this freedom here will be A1 is 1, alpha 1 is like half time step h/2, and the beta 1 will be half increment, right? So h/2 times some f. Okay, so for that one, which means the algorithm is this, you start with omega 0 equals to alpha, and then to update from omega I to omega I plus 1, the right-hand side, you need to fill in this thing with the proper A1, alpha 1, beta 1. So for this case, A1 is 1, we have 1 here. Alpha 1 is h/2, so we have h/2 here. And the beta 1 is h/2 times I of I ty, t is ti, y is omega I, right? So that's how you do from I to I plus 1. And this is the midpoint. And the student need to open this file, rk2 midpoint.m, and fill in a blank here. So they need to show what is the yn plus 1 for that, right? Okay, so this is the midpoint method. And once the student finish that part, they can run the simulation with this option of the solver, and then the result will look like this red one. So as a comparison, the Taylor of order 2 is the yellow one. There are also other two options, which means you have different choices for A1. Remember, we have this. You have different choices for A1, A2, alpha 1, beta 1, right? So A1 here is a half, and A2 here is also a half. So it's like average between these two f functions. And alpha 1 is h, which means it's here, right? So this is h, and this is beta 1 is hf. So this is hf at ti omega. This is like average. And the Hume method is like we take these two, we take two different points, one at the ti, another one at like 2/3 time steps, and then with proper weighted average, so this is like 1/4 and 3/4, then you get a good balance to get second order. So this is called the Hume method. And the student also required to modify the files for these two solver. So they are listed in rk2 mod Euler and rk2 Hume. So fill in the blank, fill in the blank. Basically, they need to fill in the blank like how they code this part, right? So that's rk2. And also we list a very popular rk4 here. So by rk4, which means we have 4 increments, k1, k2, k3, k4, and then to update omega I to omega I plus 1, you kind of need to have a weighted average of this, weighted sum of this k1, k2, k3, k4. So what is k1? K1 is purely increment from the previous time step, h times f evaluated at ti omega I, and k2 is based on this k1. So you have h times f evaluated at a half time step, and also for the second option, the y there, the y location, you need to have omega I plus a half of k1. That's the increment, approximate of increment. And for k3, you need to be aware this is k2, and for k4 is based on k3, right? And then the weighted average is like 1/626, 1/3 and 1/6, right? Okay, so the midpoint actually is a special case for this. You just have K2 here, right? So that's how you see this K1, K2, K3, K4. And the students are required to look at the RK4.m and fill in a blank for this sentence. Well, in order to assign this value, they also need to have some previous lines so that they have K1, K2, K3, K4 calculated, and then they have the yn plus 1 equals to something to finish the coding. So again, the same problem, same example. The student can run the result once the code is done, and they will get the results, which is quite close to the exact solution, right? So this is how it looks like. So the next thing the student can do is they can use this app to actually check if the solution is the so-claimed second order, fourth order, right? So what they can do is they can increase the number of n, or meaning decreasing the size of time step h, like slowly, and they can see how the order change respect to that, right? So for the fourth order, which means each time you reduce the size, the arrow is like amount like h to the power 4. So that means if you reduce the size h to a half, like h/2, then the arrow is expected to be reduced by 1/2 to the power 4, which is like 1/16. So you can try with that. And as a demonstration, here is actually the arrow of this RK4 with different h. So here's the h, here's the arrow. And this is a log-log plot, which will give you the order by just look at the slope here. So if you look at the chart, the plot here, you can easily figure out the slope here is 4, and that will actually validate the order of this algorithm is 4 for this problem, right? So student can play with it and see if they can get something similar to this. Okay, so that's the end of this this lecture file. Yeah, so that's what we want to do with this module, and what is the goal, what is the method, some details of the method. Okay, that's it.